Hey guys, okay, this is lecture 4 of unit 7 on moment of inertia. This is the last lecture of the unit, okay? And it's not a very long one, but let's get into it here. Sometimes students struggle with this material a little bit. Okay, so today we're going to talk about how mass can appear to change for a rotating object. We're going to solve for moments of inertia, and we're going to find angular acceleration for rotating objects with different shapes, okay? We're going to do some demos in class, but I'm just going to get you kind of oriented here. All right, this up a little bit. All right, an object's resistance to motion, or sorry, not motion, rotation is called moment of inertia, okay? This is the linear equivalent of mass. So the more moment of inertia an object has, the harder it's going to be to get it to spin. So it's sort of like, you know how force is to torque is the same as mass is to moment of inertia. And we always use MOI, okay? So the more moment of inertia an object has, the harder it is to get it to spin or to stop it from spinning, okay? Sort of like the more mass an object has, the harder it is to get it moving or to stop it from moving. It's the same idea, but this is just rotating. Mass is linear, okay? Now, the moment of inertia can be calculated for an object based on its shape. This is the chart, okay? So you have solid cylinder or disc. This would be used for like a wheel or a CD or something like that. A hoop, where the mass is all around the outside. A solid sphere, okay, like a lacrosse ball or something. And then a rod. And then these ones are the same shapes, but they have different axes. So if you can see this axis, this means that this one's spinning this way, this one's spinning this way, this one's spinning, this way, this one's spinning around that center axis. This one now is spinning around that center axis, around the center axis, not spinning like this, okay? Around the center axis. So different axes, okay, give different moments of inertia. Moment of inertia, we use the letter I, okay? That's the variable. And the unit, based on all of these, is mass times r squared is in all of these, or L squared. So it's kilogram meters squared. Okay? Kilogram meters squared. That's the variable, that's the unit. All right, so this just shows you how to calculate it based on the shape of the object. So the problem is going to tell you what kind of object it is, and then you're going to use the correct equation to solve for it. All right? So in the example below, we're going to solve for 3 different, a hoop, a cylinder, and a sphere. We're going to use this row the whole time, okay, around these axes. All right, so find the moment of inertia for a hoop, a solid cylinder, so let's and a sphere, each with a mass of 1 kilogram and a radius of 2 meters. So we just had to plug into the right equations here. Okay, so for a hoop, go up here, we find the hoop. Hoop, the I is equal to mr squared. Okay, so we're going to go 1 times 2 squared equals 4 kilogram meters squared. So the moment of inertia for that hoop is 4. For a solid cylinder, that's here, okay, it's going to be I equals 1/2 mr squared. So we do the same thing, we plug in 1, 2 squared. That's 4 cut in half is 2 kilogram meters squared. Okay, so it has a smaller moment of inertia, meaning this one would be easier to make it move. The hoop would be harder to make it rotate. Okay, and then for the sphere, 2/5 mr squared. Okay, you will always be given this chart, by the way. You will never have to memorize this. Equals 2/5. M is 1, R is 2. If you plug that into your calculator, you get 1.6 kilogram meters squared. So the object or the shape that is easiest to get it to rotate or spin is this one, the sphere. The hoop would be the hardest to get it to rotate or spin. Okay? All right, let's go to the back. All right, so Newton's second law describes an object's change in motion. Remember how it was in linear form. It was F equals ma. in linear form. Okay. For rotational form or angular form, it's going to be torque equals the equivalent of mass, but rotational is the moment of inertia, and the equivalent of acceleration for rotational motion is alpha. So it's torque equals I alpha, just like force equals ma. The units for torque are still newtons times meters. Newtons times meters. Okay. All right, let's do an example here. So a solid steel wheel with a mass, so solid steel wheel, so that shape would be a disc, solid disc. So we're going to use 1/2. I'm going to make a note of that. I is going to be 1/2 mr squared. Okay, so a solid steel wheel, that tells us what type of moment of inertia we're going to have, has a mass of 15, a diameter of 0.44, but I don't like diameter, I like radius, so I'm just going to cut that in half. It starts from rest, so initial velocity is 0. Okay, remember we're using angular. Suppose you want to increase the wheel's rotation to, so this is the final rotational speed, 8 revolutions per second in 15 seconds. Now I'm going to change this to radians per second because I don't like having revolutions. So in order to do that, 1 revolution is 6.28 radians. So I'm going to multiply, and I'm going to get 50.24 radians per second. Okay. What is the torque required? Okay, so we're looking for torque. Well, we know torque is equal to I alpha. We also know, remember, this is from before. Let's just remind ourselves that torque is also equal to force times the moment arm, right? The length of the moment arm times sine theta. Okay, so we don't have the force and we don't have the length of the moment arm, so we're not going to use that one. Okay, so we're going to use this equation because we do have information about the moment of inertia and we have some information where we could find alpha. Okay, so it's going to be equal to I alpha. I we can find. It's 1/2, and is 15. R is 0.22 squared. So if we solve for that, we get I equals 0.363 kilogram meters squared. Okay. Solving for alpha, we would have to use our kinematic equations. So we'd use omega final equals omega initial plus alpha t. We have omega final, which is 50.24, equals 0 plus alpha times 15. I would divide by 15 and get alpha equals 3.35 radians per second squared. Okay. Now I have I and I have alpha, and I can solve for torque. So I get 0.363 times 3.35, and I get 1.22 newtons times meters for the torque. Okay. Now it says if, in part B, if the strap is applied outside of the wheel, how much force must be applied? So you can imagine here's the wheel, okay, and there's some sort of force applied outside, out here, okay, and this is the force. The center of rotation, or this is the force. The pivot point would be in the center of the wheel, so the distance from the pivot point to the force would just be the radius of the circle, okay, and we want to know what force we would need in order to get this torque. Well, I reminded you earlier that torque is force times distance, from pivot point to force, sine theta. This angle is 90. Okay, so sine 90 is 1. So we would say torque equals Fr sine theta. 1.22 equals F times, again, the radius is the distance from the pivot point to the force. So this is the same as the radius. Sine 90 is 1. So if we solve for force, we get 2.77 newtons. Okay. Okay, let's do one more. Okay. A golfer swings a club. Okay, so here's the golf club. Alright. Okay. Accelerating it from rest to 20 revolutions per second. Again, I'm going to instantly change that to radians because I don't like revolutions per second. So that's actually equal to 126, 126 radians per second. Okay. In 0.15 seconds. The golf club shaft is really light, no mass. Okay, so that means we don't include it in the moment of inertia. So this thing is like rotating around like this. Okay. It has a length of 1 meter. Okay. And the club head has a mass of 0.8 kilograms. So the mass is 0.8 kilograms. The radius of the circle, you can see if this club swings around, the radius of the circle is equal to the 1 meter. Okay. Find the torque that the player applied. Okay. We're going to do it the same way we did this one, except for now we have to figure out how is this, what shape is this basically represented by. We're ignoring the golf club part. We're just only taking into account the head. So if you can imagine, as this goes around, it's like a mass. And if you drew one of these at every single spot, you would notice that this actually becomes sort of like a hoop, right? As the golf club travels around, you can imagine this becomes sort of like a hoop of mass. So we're going to treat it like a hoop, okay? Which means that if we go back to our table here, our I is equal to mr squared. Okay, so let's solve for I. M is 0.8. R is 1, so 0.8 is our I. Okay. Finding our alpha, because remember we want torque, which is equal to I alpha. So we need to solve for both those things. So alpha is going to be omega final equals omega initial plus alpha t. Omega final is 126, 0. Alpha 0.15. If you solve that, you get alpha equals 840 radians per second squared. And now we take this torque, we set it equal to I alpha, 0.8 times 840, and we get torque is equal to 672 Newton meters. Okay, so that is all we have to do. We'll go over some more examples in class. All right.